Dr. Hansen here. I will be talking about hemoglobin and myoglobin. The talk is a little bit complicated, but I think if you take your time and try to understand the concepts, it will become a lot easier to memorize this stuff, which is very important. And in fact, before you listen to this preview video, I recommend that you go to the pre-preview videos. There's a link here to a website that has some very nicely done videos which give some very graphical understanding about the cooperativity of hemoglobin. Some of the learning objectives listed here will be covered in the preview video. At the very beginning, you need to be able to interpret plots, in this case, of oxygen binding to hemoglobin versus oxygen concentration. And you need to be able to apply those interpretations to biochemical principles. The cooperative binding of oxygen to hemoglobin is in parallel to the cooperativity of many enzyme activities, so this goes beyond just the hemoglobin talk. Hemoglobin is cooperative and enzymes are cooperative because they exist in two possible states, a T state and an R state, each with different affinities for the substrates. In turn, the equilibrium between the T state and the R state will be affected by the concentrations of oxygen, carbon dioxide, protons, and 2,3-bisphosphoglycerate. And at the heart of today's talk, I want you to understand how the concentration of each of these compounds will favor either the T or the R state. Not only is the concept of cooperativity much broader than the talk on hemoglobin and myoglobin, but the role of hemoglobin in your blood in transporting oxygen to your tissue is going to be very important in hematology next year, where we'll talk about anemia, the role hemoglobin plays in it, as well as a bunch of mutant forms of hemoglobin which lead to anemias. And so you really need to understand how hemoglobin works in order to understand the mutant forms. Hemoglobin transports oxygen, and in order to transport oxygen, it needs to bind to it, and its binding is cooperative. That's very important because in the 1 second that hemoglobin spends in the lungs before it goes to the rest of the body, it needs to go from an oxygen depleted state to an almost completely bound state so that it can carry oxygen with it to the rest of the body. In order to understand hemoglobin, I want to look very briefly at its structure. Hemoglobin is a tetramer of globin proteins that are homologous to the monomeric myoglobin. Myoglobin found in muscle, hemoglobin found in blood. And just as myoglobin binds a single heme group, so hemoglobin binds to 4 heme groups. The oxygen will bind specifically to the heme group. Hemoglobin is actually a dimer of dimers. There's an alpha 1 beta 1 heterodimer and an alpha 2 beta 2 heterodimer, and the two of them come together to form a tetramer. The tetrameric structure of hemoglobin is needed to give it cooperativity. And right now I want to compare how hemoglobin binds oxygen to how myoglobin does. So if we look at myoglobin, and we're looking at this binding curve to interpret it as a learning objective, I first just want to remind you, when you see these plots, don't just think I'm going to memorize the shape of this plot, because I do think you will see a number of plots on the board exam. And you can't just interpret the shape, you need to know what it is. So, whether it's in a talk I'm giving, the physiologists, a test, a board exam, I hope that whenever you see any type of plot that you pause and slow down and actually read the axes and think about what they mean. Many curves with the same shape will mean completely different things depending upon the axes. It turns out that most of the plots I'll be showing plot how saturated myoglobin becomes with oxygen as a function of oxygen concentration. And in this figure, the oxygen concentration is in millimeters of mercury, and the saturation of myoglobin is in terms of percent saturation. I know that you're all familiar with this type of hyperbolic plot. But will you please pause and describe why this has this shape? Why isn't this simply a linear plot that the more oxygen you have, the more myoglobin will be bound? Please explain, but I'll go ahead. To be clear, this is all about enzyme saturation. Relative to oxygen, there's a very small amount of myoglobin. Therefore, when there's no oxygen, there can be none bound. And as you add just a little bit of oxygen, there's quite a bit of myoglobin to be bound, and there's so much oxygen that they just bump into each other, and the more oxygen, the more quickly you will bind, such that there's a linear growth to begin with. But the limited amount of myoglobin begins to get filled up, and now even though the oxygen concentration is getting higher and higher, there's not as many myoglobins to find. And of course, eventually you will approach 100% saturation, but you can never be at exactly 100% saturation because there's always oxygen coming and going. And when you have 99.9% bound, there'll still occasionally an oxygen come off and another one has to come back on. To highlight this hyperbolic nature of the curve, I point out that when you start at 0 and add just a little bit of oxygen, there's a big increase in the fraction that's bound. But as you begin to bind half of it, now you can double the amount of oxygen again, and there's not as big of an increase. Double it again, still it gets a little bit bigger, but not by as much, and eventually you will approach the asymptote. Now I want to compare the hyperbolic binding curve of oxygen to myoglobin to the binding of hemoglobin. Now, first of all, will you tell me which binds oxygen more tightly? It's a real easy question, but you really want to physically understand these curves and not just think about their shapes. So, of course, the way I see this is I would go to any one concentration of oxygen and look. Okay, let's see, maybe 30% bound to hemoglobin, 90% to myoglobin is bound up. So obviously hemoglobin binds a lot lower. That's the first most important difference between hemoglobin and myoglobin, is that hemoglobin has a reduced affinity. The next question is to compare these two shapes. Myoglobin has a hyperbolic curve in a tighter binding to oxygen. Hemoglobin has what's called a sigmoidal shape. And again, sigmoidal for the Greek letter S, because it's kind of a really badly drawn S where it curves one direction, there's an inflection point, and then curves the other. That's why they call it sigmoidal. Now, how is this going to affect the binding of oxygen relevant to physiology? For example, in the lungs, will hemoglobin bind oxygen more tightly, or in remote tissue will it bind more tightly based on this figure? So we just take a look. Lungs have, of course, a high concentration of oxygen, and at that concentration, hemoglobin has a much higher affinity for oxygen. And in remote tissue, it has a much lower affinity. If you didn't have hemoglobin, and instead your blood was using myoglobin to transport oxygen, you can see that myoglobin binds a little bit more oxygen than hemoglobin. How effective would that be? And please pause and answer. This is the most basic thinking about hemoglobin. Although in the lungs, myoglobin has a slightly higher affinity for oxygen than does hemoglobin, so it could be almost 100% bound up. Hemoglobin might be 99.9. What happens is in remote tissue, the myoglobin cannot release the hemoglobin. In other words, in remote tissue, it still has a very high affinity, whereas hemoglobin's lower affinity means that oxygen can be released. So this is at the heart of thinking about hemoglobin cooperativity, that it's not how much oxygen you can bind, it's also how much you can release that really matters. Myoglobin binds more, but if it can't release it, it's not going to help you. The cooperativity of hemoglobin is so fundamental to its role that I want to use the dump truck analogy. If you're totally familiar with the concept, you should speed through this part. But I want to point out that there's two types of dump trucks in this story. We have one that has good suspension, but a bad lift. So with the good suspension, it can be loaded completely full of sand. You drive it across town, but you can't use the lift, so you can't really unload it. Maybe you can scrape 10% off the top. So whereas one truck is 100% full and moving across town, it's only delivering 10% of the load. We have another truck that doesn't have good suspension, so you can only load it about half full of sand. But the lift is fine, and therefore, when you go across town, you lift, all the sand comes out, it's delivered a complete payload. So the truck that carries the least can actually deliver the most, and this is how hemoglobin works. Now I want to take a look at this tetrameric state. Now, this binding of oxygen to hemoglobin, this cooperative behavior, is dependent largely upon the tetrameric shape. And I want you to be familiar with the overall tetrameric shape, and I want you to be familiar with the terms T state, which is tight or tissue, and R state, which is relaxed or respiratory. And notice the shape. The tight state has a donut shape with a large hole in the middle. The R state has collapsed, and there's a very small hole in the middle. This has a lot to do with how oxygen is bound. Now, I would look at this and I'd say, well, the tight state, that must bind tightly, right? Well, no, it doesn't work that way. The T and R states don't just refer to hemoglobin, but there's a number of cooperative proteins where T means the tight and R means relaxed. And T actually means low affinity and R means high affinity. Why is that? Well, the T state in the case of hemoglobin, tight, is really referring to the interfaces between each alpha 1, beta 1, alpha 2, beta 2, beta 2, alpha 1 monomer. These interfaces are tight, and therefore they stabilize this expanded donut-shaped structure. In contrast, the relaxed state, these interfaces have been weakened so that the structure collapses. Another thing about tight versus relaxed, which type of a protein do you think will bind more tightly to a compound? One which has a rigid structure or one which has a floppy structure? Well, it turns out that the floppy structure almost always is needed to bind to a substrate. And the reason is that, first of all, the substrate has to get into the binding site, which might need things to move around. And then once the substrate's in the binding site, the floppiness allows the protein to close around it. Being relaxed and a bit floppy makes it easier to bind oxygen, whereas being tight or rigid makes it harder to do that. Regardless, as a physician, you might find it easier to think T state means tissue, because that's where you want low affinity for oxygen. And you might want to think R state means respiration, because the lungs is where you want to have the high affinity. But it is useful you should know about this donut shape. Now let's take a look at this. Here I'm showing an oxygen molecule coming in. And because this is in the donut or tight state, it has low affinity, so oxygens come in and they go back out, they don't have much affinity. However, sometimes two might bind at the same time, and when this happens, actually that increases the affinity for additional, which increases affinity for additional, which increases affinity for additional. So in other words, when oxygen binds to hemoglobin, it increases the affinity of hemoglobin for a second oxygen, which even more increases the affinity for a third one. So therefore, hemoglobin tends to be either all completely bound in oxygen or not bound at all. Let's take a look at that here. When the first oxygen binds to hemoglobin, it has a certain affinity. After it binds, then the second one actually has a threefold greater probability of binding. And when the second one binds, that increases the affinity 20-fold. And when the third one binds, it's about a 300-fold. What about when the fourth one binds? What's it going to do to the affinity to bind the next oxygen? Well, actually, you only have 4 sites, so it's kind of a moot question, but a dramatic change in affinity for oxygen. How will the cooperativity of oxygen, meaning the more oxygens which are bound, the higher the affinity is, how will that affect the binding of oxygen when you're in the lungs? The way to think about the sigmoidal curve of cooperative hemoglobin is that really it's composed of 2 different curves. A high affinity curve that's almost identical to myoglobin. and a low affinity curve that's also hyperbolic like myoglobin, but with a much lower affinity. And so in the lungs, where there's a lot of oxygen, more oxygen binds to it, favors binding of another, favors binding of another. There's so much oxygen that almost all four are bound and they're in the R state. So let's take another look at this. We look at the part of the hemoglobin binding curve that's very parallel and almost identical to the myoglobin binding curve, and we can see this accounts for the upper part of the sigmoidal shape. And this is sort of in the lungs or at high oxygen. We look at what's happening in the tissue where most of the oxygen has been taken away by the cells. There's not much oxygen around, and therefore hemoglobin has converted to the tight state that doesn't like to bind oxygen, and it fits the lower curve. Now, as you leave the lungs, a little bit of the oxygen is gone. There's not as much. Therefore, some of the hemoglobin is in the high affinity state and some is in the low affinity state. The further from the lungs you get, the more like the low affinity state. So we have essentially high affinity state, even transition to low affinity state. So again, the sigmoidal shape is essentially a combination of a high affinity and low affinity hyperbolic curve. We are going to look at how the concentration of oxygen, carbon dioxide, protons, and 2,3-bisphosphoglycerate affect the affinity of hemoglobin for oxygen. In order to prepare for that, we've already gone over it. Will you right now answer, does high oxygen concentration stabilize the T state or the R state? And how does that affect oxygen affinity? You're thinking high O2, we're in the lungs. What do you want to do in the lungs? You want to pick up oxygen. Therefore, high O2 binds to the hemoglobin, stabilizes the high affinity state. Therefore, it definitely favors the R state. How do you get this change? Mechanistically, structurally, what is happening here? And here I'm showing a picture of globin with a heme group bound to it, and you'll notice some nearby histidines. And there's an iron in the middle of the heme atom, which is chelated by a nitrogen and by the nitrogens in the heme. It is very easy for oxygen to come along. Oxygen, is it electronegative or electropositive? And is iron electronegative or electropositive? Oxygen is about the most electronegative atom out there. It wants electrons. Iron's a metal. It can give up electrons. So they sense each other and they form a bond. So here we're showing without oxygen, and here I'm showing that the oxygen has come down. It really likes the electrons that iron has, and iron 2 here releases its electrons into this bond and becomes very close to iron 3. Now there's something else interesting about that. When oxygen binds on this side of the heme group, what happens is the iron moves. Iron 2 has more electrons than iron 3, therefore a bigger shell, and it is too big. It sterically cannot fit in the middle of the heme group. The heme group, of course, is completely locked all around into the globin, therefore it's not going to move and the iron can't move. However, when the oxygen comes and withdraws electrons away from iron 2 to make it almost iron 3, then this no longer is sterically kept outside the heme group and it slides in, which allows the histidine, which is chelated to the iron, to move. It turns out in turn that that histidine residue, here I'm showing a pink oxyhemoglobin with colored blue nitrogens, and it's connected to the small iron atom, and you can see that it has moved up into the ring, and at the end of the helix is an interface between alpha and beta subunits. Therefore, this slight motion, only about an angstrom, perturbs the interface. In contrast, you can look at the gray helix with the gray histidine with the large iron 2, the large green sphere here is going to be in a different position. Perturbs the interface. How's that going to affect it? Well, let's take a look here. The oxygen, O2 in red, comes down. The iron senses it. They bond. The iron shrinks, comes up to the oxygen. The histidine moves. When the histidine moves, that perturbs the interface interaction at that helix, which dramatically changes the structure from the relaxed state that's all collapsed in red to the T state that's like a donut in wide open. So that's how oxygen literally structurally stabilizes the collapsed small hole relaxed form, whereas an absence of oxygen would tend to stabilize
the T state there, wouldn't like to bind oxygen. There's only really 4 of these we're going to look at. Let's look at carbon dioxide. Does high carbon dioxide concentration stabilize the T state or the R state? I'd like you to pause and answer it. Now I'll answer it. Where is there a lot of carbon dioxide? Is that in the lungs or is it in the remote tissue like the tips of your fingers and toes? In the lungs, you have a lot of oxygen. You're exchanging it for carbon dioxide. The carbon dioxide concentration in remote tissue is much higher than in the lungs. The remote tissue also is where you want to release the oxygen. So it makes sense physiologically that CO2 is going to favor the T state because that's the tight state which will release the oxygen. And let's take a look at a plot of this. If you're having trouble understanding this, we're going to do the same thing with each of these compounds, so don't be afraid to slow this down and stop and think a little. One of these plots is going to represent the saturation of hemoglobin in a given concentration of oxygen, in one case in a high CO2 concentration, in another case in a low CO2 concentration. Can you tell me which is T and which is R? We look at the two. Which is the lower curve? The lower curve is the one that's down here. That means it has lower affinity. At every given concentration, it is lower than the other curve. The lower curve will represent the T state, and the upper curve will represent the R state, because the R state is going to have higher affinity and therefore will be more bound at a given concentration. Which of them represents low CO2? Well, let's say which represents high CO2. High CO2 means low affinity for oxygen, so the lower curve will represent low CO2. Now, interestingly, I like to look and say, okay, what fraction is saturated at a given concentration? I need to see which is up and down, right? The physiologists like to think left and right. So they would refer to the high CO2 curve, to the tight state, which has lower affinity, as being right shifted. And the one with higher affinity they would refer to as being left shifted. You can refer to it that way if you want. Certainly that might help you understand how to compare my discussion of this with theirs. Interestingly, let's say that you're running. The tissue which is burning the most oxygen is going to have the highest concentration of CO2 and the greatest need for new oxygen. So it isn't just that CO2 says, give me oxygen. The more CO2 you have in a given tissue, the stronger the signal is to get more oxygen. As long as we're looking at oxygen binding to hemoglobin here, I wanted to mention that CO2 does not bind to the same site as O2. Interestingly, carbon monoxide does bind to the same site. So in other words, O2 binds to the iron that's in the heme group, and it binds at an angle, you'll notice, such that one of its oxygens interacts with the iron and the other interacts with the histidine residue. Actually, the histidine kind of interferes with the O2 binding a little bit, destabilizes it. In contrast, CO, carbon monoxide, has a very different configuration than O2, and therefore it sticks straight up and nothing interferes with its binding. So CO, carbon monoxide, has a much higher affinity for hemoglobin than does O2, and it's one reason carbon monoxide is so toxic. But then your question might be, where does CO2 bind? Interestingly, CO2 covalently links itself to hemoglobin, and it binds to the N-terminus of the hemoglobin molecule on the nitrogen at the N-terminal valine. Does this remind you of something? The ammonia, there's a pair of electrons here that can interact with a carbon. Electrons resonate up here, and now we have a carbamate. Blood is very good at binding CO2 there, and most of the CO2 being moved out of your blood is being bound to the hemoglobin and being transported out. How might this then alter the affinity of hemoglobin for oxygen? How might this perturb the structure? Well, I'll just say that an amine is very different from a carbamate. Can you tell me chemically what's different between them? What's the typical charge on an amine? It's normally going to be protonated and positively charged. A carbamate will either be negative or perhaps neutral. Without CO2, we have an N-terminus that's near a lysine where these two positive charged amines are repelling each other. In contrast, if we have a carbamate, we have a negative and a positive charge which could actually attract each other. This could thereby perturb the structure of the hemoglobin tetramer. This part is not a learning objective, but I just want to say it makes sense that CO2 would physically change the hemoglobin in a way that could affect its structure.
We will again look at how the concentration of carbon dioxide affects the cooperativity of oxygen binding to hemoglobin, to be sure that you understand the logic behind the physiology. Also, we will take a look at how pH affects the cooperativity. And before you come there, I would like you to think a little bit about where in your body is the pH high, where is it low? How should that correspond with regions of the body that will need oxygen released and that won't need oxygen released? Accordingly, does high pH or low pH favor the T state or the R state? Does it favor tight binding or loose binding? All of those terms should make sense. Please go ahead and work on that some, trying to figure carbon dioxide or pH out, or the cooperative oxygen itself. And I look forward to seeing you. Thanks.